Welcome you all for the online class on Control Systems Engineering. In today's class, we are going to see a problem in electrical analogous to mechanical translational system. So in the previous class, we have seen one problem in the electrical analogy of mechanical translational system. Okay. Today we are going to see one more problem in this electrical analogy of mechanical translational system. Okay, so here the question is, write the differential equation governing the mechanical system shown and draw the force to voltage and the force to current electrical analogous circuits and verify by writing mesh and node equations. Okay, so this is the problem. The given system is a mechanical translational system because it uses the elements of mechanical translational system, that is M, B as well as K. Okay, and in this question there is no input signal, that is linear force F. Okay, so no need to consider the input, only we have to consider the output for every reference elements M1, M2 as well as M3. Okay, here totally 3 number of masses. Okay, and the frictional coefficient B2 as well as B3 are represented without its symbol. Okay, there will be a friction between M2 as well as M1 and also between M3 as well as M1. Okay, that is simply represented by a letter B2 as well as B3. Okay, now before starting the problem, what we have to do is, for each reference element, that is mass M1, M2 as well as M3, we have to assume the output, displacement as well as velocities. Okay, in electrical analogy, we are considering the output as an rate of change of displacement, that is velocity, for mechanical translational system. Okay, so for mass M1, the output will be x1 and the corresponding velocity will be v1. For mass m2, displacement will be x2 and the corresponding velocity will be v2. Then for mass m3, the displacement will be x3 and the corresponding velocity will be v3. This we have to mark, okay, by redrawing the question. So now we have to write the input as well as outputs. So here there is no input signal, so no need to write the input. Okay, only we have to write the output. So the output displacements are x1, x2 as well as x3. Okay, output velocities are v1, v2 as well as v3. Okay, so now what we are going to do is, for mass m1, m2 as well as m3, separately we are going to draw a free body diagram and we are going to derive the differential equation governing the system. Okay, similar to the previous problem. Okay, so see here, the free body diagram for mass M1 is given by. So to draw the free body diagram for mass M1, first we have to represent the mass M1 in a square box. Okay, so this is the problem question. So by seeing this question, we have to draw all the applied as well as opposing forces. Okay, immediately by drawing the mass M1, we have to represent the corresponding outputs. For mass M1, the outputs will be x1 as well as v1. Okay, so immediately here we have to represent x1 as well as v1. Okay, now what are the applied as well as opposing forces for mass M1? So for this mass M1, there is no applied force. Okay, so no need to represent the applied force here. Now we have to see all the opposing forces. For mass M1, its own opposing force will be represented by Fm1. Okay, see the question. Then what are the elements which are connected only to this mass M1? K1 as well as B1. So the corresponding opposing forces will be Fk1 as well as Fb1. Okay. Now we have to see the elements that are connected between the mass M1 as well as the other masses M2 and M3. Okay, that is B2 as well as B3. Okay, so correspondingly we can write FB2 as well as FB3. Understood? Okay, this we know already. Okay, now we have to write the formula for all the opposing forces. Here the opposing forces are totally 5 number of opposing forces, isn't it? First one is Fm1. So this is not Fm, Fm1 will be equal to m1 into d square x1 divided by dt square. So these are all the formulas used for finding the opposing forces. Okay, the value of Fm will be m into d square x by dt square. Okay, so here it will be m1 into d square x1 divided by dt square because the output here is x1. Now the next opposing force will be Fk1, isn't it? K1 is connected only to this m1, not related to m2 as well as m3. So directly we can write the formula for Fk. What is Fk? K into x. Okay, so here it is K1. So K1 into x1, the corresponding displacement. Then what about the next element? That is B1. So the opposing force will be Fb1. Yeah, B1 is also connected to this m1. Okay, not related to m2 and m3. So for writing the value of Fb1, we can directly write the formula B1 into dx1 divided by dt. Okay. Now the next opposing force will be Fb2. So what is Fb2? The B2 is connected between M1 as well as M2. So the value of Fb2 can be written as B2 into difference in displacement. That is d by dt of x1 minus x2. Okay. So B2 is connected between M1 as well as M2. So we have to write the corresponding difference in displacement. Okay. Now we are writing the equation for M1. So we have to consider the corresponding displacement x1 first. Okay. Then you have to write the displacement for M2, that is x2. Okay. And the last opposing force is Fb3. What is the formula for Fb? B into dx by dt. This B3 is connected between M1 as well as M3. So we have to write the difference in displacement, that is x1 minus x3. Okay, B3 into d by dt of x1 minus x3. In this way, we can write all the opposing force values. Now, using Newton's second law, in this mass, what about the applied force? Here there is no applied force. All the forces are opposing forces. Now, the sum of all the opposing forces will be equal to 0 because there is no applied force here. Okay. Now, we have to substitute all the values of opposing forces in this equation and we will get the equation like this. Okay. So, this will be equation number A. That's a differential equation. Okay. Now, we have to replace the displacement by its corresponding velocity because for analogous circuit, we are considering the rate of change of displacement. Okay. So here we know the relationship between x as well as v. Okay. Using these formulas, we can easily replace this x by v. Okay. So the first element is m1 into what is d square x by dt square. D square x by dt square is nothing but dv by dt. Okay, here we have d square x1 by dt square. So it will be dv1 divided by dt. Okay, then plus k1 into what about x in terms of v? See the first equation, x is equal to integral v dt. Okay, here we have x1, so integral v1 dt. Okay, the next term is v1 into dx by dt. What is dx by dt in terms of v? See here it will be v. Okay, here we have dx1 by dt. So here we have to write it as v1. Okay, the next element is b2 into d by dt of x1 minus x2. So this can be written as dx1 by dt minus dx2 by dt. What is dx1 by dt in terms of v? It will be v1. dx2 by dt will be v2. Okay, so here we have a bracket. So here also we have to write the bracket. Okay, then the last term is v3 into dx1 divided by dt. That is nothing but v1 in terms of velocity minus dx3 divided by dt. That is nothing but v3 in terms of velocity. Okay, that is equal to 0. Okay, so now we have to mark this as equation number 1. Okay, so similar to this mass m1, for mass m2 and m3 also we have to draw the free body diagram and we have to obtain the equations. Okay, now Consider the mass M2. So this is the question. Here, by seeing this question, we can draw the free body diagram of mass M2. So first we have to put the square box like this to draw the free body diagram. Inside that we have to write the mass M2. See here, this is mass M2. Whether there is any applied force, here there is no applied force. So no need to draw the applied force here. All the forces are opposing forces. What are the opposing forces? First we have to write the own opposing force, that is Fm2. Then what are the elements connected only to this M2? None of the elements, isn't it? So we have to see the elements that is connected between the mass M2 as well as other masses. Okay, so if you are considering this B2, this will be connected between M1 as well as M2. So the opposing force will be FB2. Okay, now the other elements are K23. So it will be FK23. Okay, here two letters are there. Now B23. So this will be FB23. Okay. So now these are all the opposing forces. We know the formula for opposing force. Okay. So these are all the formula for opposing force. Okay. So now using these formulas, we have to write the value of each and every opposing forces. Fm2 is equal to m2 into d square x2, because this displacement is x2 divided by dt square. Okay. Then what about the value of fb2? So for that we have to see where this B2 is connected. It is connected between M1 as well as M2. So we have to write the difference in displacement. Now we are writing the equation for M2. So you have to write the displacement for this M2 first. That is x2 minus x1. Okay. So similarly, what about the value of next opposing force Fk23? Fk23 is connected between, that is K23 is connected between M2 as well as M3. So while writing the opposing force, we have to write the difference in displacement, that is x2 minus x3, because we are writing the equation for M2. Okay, so Fk23 will be K23 into x2 minus x3. Now the last one is Fb23. Fb23 is connected between M2 as well as M3. Okay, so we have to write the difference in displacement in the formula. Okay, so now we have to apply Newton's second law in this mass. What about the applied force? There is no applied force. All the forces are opposing forces. So the sum of all the opposing forces will be equal to 0. We have the equation for each and every opposing forces. We have to substitute all the opposing forces here and we will get the equation like this. So this is an equation B. Okay. Now in this equation we have to replace the displacement by velocity. Okay, because in electrical analogy we are considering the rate of change of displacement as an output. Okay, so now what we have to do, we know the formula for the relation between displacement as well as velocity, that is displayed here. Okay, so using this we have to replace each and every displacement in this equation B into its corresponding velocity. The first term is m2 into d by dt of v2. Okay, because d square x by dt square equal to dv by dt. Here we have x2, so correspondingly here we have to write it as v2. Then what about the second term, v2 into dx2 by dt, that is nothing but v2, minus dx1 by dt, that is nothing but v1. Then the third element is k23 into, what about x in terms of v, that is x will be equal to integral v dt. So x2 minus x3 will be integral of v2 minus v3 dt. Okay, now b23 into dx2 divided by dt, that is nothing but v2, minus dx3 divided by dt, that is nothing but v3. Okay, this is equal to 0. Now this is equation number 2. Okay, similarly we have to derive the equation for mass m3. Okay, now we are considering the free body diagram for mass m3. So to draw the free body diagram, first we have to represent the mass. Immediately we have to write the corresponding output displacement as well as velocity. Now see this mass m3. In this mass m3 there is no applied force. No need to draw the applied force here. All the forces are opposing forces. Now we have to draw each and every opposing force one by one. For mass m3, its own opposing force will be Fm3. Then what are the elements connected to only this mass m3? None of the element. Okay, now the different elements are connected between m3 as well as m2 and m1. Okay, so now if we are considering k23, it will be connected between m3 as well as m2. So the opposing force will be fk23, then b23. FB23 and here it is B3. So FB3. So there will be an 4 number of opposing forces. Now we know the formula for opposing force that is given here. What is Fm3? M3 into d square x3 divided by dt square because the displacement here is x3. Now what is Fk23? So for that we have to see here where this K23 is connected. It is not only connected to this M3, it is also connected between this M2 as well as M3. Okay. So we have to write the difference in displacement. Now we are writing the equation for M3. So the displacement for the M3 should come first. Okay. That is x3 minus x2. Now what about B23? B23 is connected between M3 and M2. Okay. So B23 into d by dt of difference in displacement. That is x3 minus x2 because we are writing the equation for M3. Okay. So x3 should come first. Next x2. Okay. Now what is FB3? FB3 is connected between M3 as well as M1. Okay. So we have to write the difference in displacement as x3 minus x1. Okay. So in the formula for FB3 we have to write the difference in displacement x3 minus x1. Okay. Now using Newton's second law we can find we can write the sum of the opposing forces will be equal to the applied force. Okay. So here there is no applied force. All the forces are opposing forces. So we can write sum of all the opposing forces will be equal to 0. Okay. Now we have to substitute all the values of opposing forces here. Then we get the equation C. Okay. Now here what we have to do? We have to replace the displacement by velocity. So for that we have the relation here. M3 into d square x3 divided by dt square will be dv3 by dt. Okay. Then K23 that's constant. What is x3 minus x2? Simply x can be written as integral v dt. Okay. So here we have to write integral v3 minus v2 dt. Okay. Then b23 into this can be written as dx3 by dt. What is dx by dt? V. So dx3 by dt will be v3 minus dx2 by dt. That is nothing but v2. Okay. Then plus b3 into this can be written as dx3 by dt. That is nothing but v3 minus dx1 by dt. That is nothing but v1. Okay, which is equal to 0. We can mark this as equation number 3. Okay, now we are going to find the electrical analogy. Okay, so first analogy is an force to voltage analogy. So here first we have to write the formula for force to voltage analogy. Okay, so now to draw this electrical analogous circuit using force to voltage analogy, we have to see this question. Okay, so this is an question. So here we have 3 number of masses. So correspondingly, for force to voltage analogy, we have to assume 3 number of loops. Okay, so here we have 1 loop and above this mass M1 we have 2 number of loops. Okay, 2 number of masses. So correspondingly for mass M1 here we have to assume 1 loop. Then for mass M2 as well as M3 here we assume 2 number of loops. Okay. So this loop is for mass M1. Okay, initially we have to assume like this. Here in force to voltage analogy we are going to use Kirchhoff's voltage law. Okay, so for that we need a loop. Okay, so each mass corresponds to loops in a force to voltage analogous circuit. Okay, so this loop is for mass M1. Then here we have mass M2, isn't it? So here I assume the loop for mass M2 and here this is the loop for mass M3. Okay, so we can also assume this for mass M1 and this loop for mass M2 as well as this loop for mass M3. Okay, so now how will you draw this diagram from this question? So what we have to do? So first we have to assume 3 loops like this based on the structure of the input. Okay. For mass M1 we have to see is there is any applied force. Okay, similar to the procedure for drawing the free body diagram. Okay, here for M1 there is no applied force, so in this loop there will not be any voltage source because force is equated to voltage. Okay, now what are the opposing forces? Here for mass M1 its own opposing force will be Fm1 M1 then. Okay, so for M1 this corresponds to L. Okay, so now we have to draw this L1. For M1 it will be L1. Okay, now what are the elements that is connected only to this M1? K1, B1. K corresponds to C. Okay, K1 will be C1. Then B corresponds to R. So B1 will be R1. Okay, in this branch, don't draw any of the elements because this represents the ground. Okay, so the elements corresponds only to this mass M1, or the elements connected to only this mass M1 should be represented in this branch, as well as we can represent it in this branch. Okay, now this resistor, that is dashpot B2, is connected between M1 as well as M2. Okay, so B corresponds to R. So B2 will be transformed to R2 and it is connected between loop 1 as well as loop 2. So here it will be R2. Understood? Now B3. B3 is another one element for this mass M1, isn't it? So for B3 it will be R3 after transformation. Okay. So this B3 is connected between M1 and M3. Okay. So this is the loop for M3. Okay, so now here we have to, in between M1 as well as M3, we have to draw this R3. Understood? In this way, we can complete each and every element for this loop 1. Okay, now we have to see this loop 2. So to draw this loop 2, what we have to do? We have to see this mass M2. Okay, so this is the mass M2. So here there is no applied force. So there will not be any voltage source here. Then its own opposing force will be M2. Okay, M will be L, so it will be L2. So in this branch we have to draw L2. Okay, this branch as well as this branch, this is only for M2. Okay, so here we can draw L2. Now none of the elements for this M2 only. Okay, then these two elements are connected between M2 as well as M3, that is K23. What is K2? K corresponds to K is transformed into C. So here we have to write C23 in between M2 as well as M3. Okay, now the next element is B23. B corresponds to R. Okay, so it will be R23. So here you have to write R23. This K23 as well as B23 are connected between M2 as well as M3. Correspondingly, in between the loop 2 as well as loop 3, we have the two elements. Understood? In this way, we can complete all the elements in this loop 2. Okay, the elements corresponds to only loop 2 should be drawn here as well as here. Okay, now we have to complete this loop 3. So for that we have to see the mass M3. So when we are considering mass M3, there is no applied force. So there will not be any voltage source here. Suppose if you have an applied force for this M3, here you have to put the voltage source. Okay, and in the right side you have to put plus sign, as well as in the left side we have to put minus sign for the voltage source. Okay, then only the direction of current flow will match with the polarity of the voltage source. Okay, so here there is no applied force, so there will not be any voltage source in this loop. Now what are the opposing forces? Its own opposing force due to M3. So M corresponds to L, so we have to draw this L3. Understood? Now none of the elements are connected only through this M3. So we have to see the elements that are connected between M3 as well as other masses. Okay, between M3 as well as M2 we have K23 as well as B23. K corresponds to C, that is C23, and B corresponds to R, that is R23, that we have already drawn. Okay, so no need to draw it again. Okay, now for this mass M3, this B3 is connected between M3 as well as M1. So in between loop 3 as well as loop 1, already we have R3. Okay, so no need to draw it again. Understood? In this way we can complete the three loops. Understood? Okay, so after drawing each and every element in this loop, we have to apply Kirchhoff's voltage law because it is an force to voltage analogy. Okay, so for each and every loop, we have to assume the loop current. So this is an first loop, isn't it, for mass M1? So we can assume the loop current as I1. So as I told already, for each and every loop, we can assume the direction of current always in the clockwise direction. Okay. So we can assume the current direction in the anti-clockwise direction also. But if you are assuming it in the anti-clockwise direction, correspondingly you have to put the polarity and also you have to write the equation. Okay. So here we are writing all the currents in the clockwise directions. Okay. So this is clockwise and this is also clockwise and this is also a clockwise direction. Okay. So to apply Kirchhoff's voltage law along the direction of current flow, for every element we have to put plus minus. Here it is plus minus, plus minus, plus minus, plus minus, plus minus, etc. Similarly, for each and every element, we have to put plus minus along the direction of current flow. So if you are considering this branch, here you will be having the plus minus in the opposite directions. Okay, so because of the opposite direction of current flow, that is I1 is flowing from left to right and I3 is flowing from right to left through this resistor R3. Okay, similarly here also there will be two number of polarities. Here also there will be a two number of polarity for each element. So while writing the equation, we have to consider that polarity. Okay. So while drawing this diagram from this question, we have to see that we have to assume that there should be a common branch between M1 and M3, and there should be a common branch between M1 and M2. Okay, so here we have a common branch between this loop 1 and loop 3 and also between loop 1 as well as loop 2. Then only the corresponding common elements can be represented in that corresponding branches. Okay, so that's a very, very important point. After drawing this diagram, we are going to apply Kirchhoff's voltage law. Okay, for loop 1. So this is the same diagram that I have shown in the previous slide. So here this is loop 1. For loop 1, when we are applying Kirchhoff's voltage law, what will be the equation? So we can start from here or we can start from here. Okay, if we are starting from here, then after going through all the elements, again you have to end at the same point. Okay, now we can start it from here. Okay, so initially the first element is R1. Now we are applying Kirchhoff's voltage law. For each and every element, we have to write the equation for voltage. Okay, for this R1, the voltage will be, it is given in the formula. V is equal to I into R. That is I1 into R1. It is going from plus to minus. So here we have to put minus. Minus I1 into R1. Then again it is plus to minus. So minus. What about the voltage drop across the capacitor C1? That is given in the formula. 1 by C into integral I dt. Okay. So 1 by C1 into integral I1. A single current is flowing through the C1. That is I1. So I1 into dt. Then again it is going from plus to minus. So we have to put minus sign. What about the voltage drop across the inductor L? Here it is given. For inductor L into di by dt. Okay. So here it will be L1 into di1 divided by dt. That's the corresponding current. Okay. So now the next element is R3. From plus to minus it will be minus. Okay. For resistor, what about the voltage? I into R. Okay. So here R3 into, here we have to write the I value. So two currents are flowing, isn't it? So we have to write the difference in current. Okay. Because both are flowing in the opposite direction. Understood? If both the currents are flowing in the same direction, we have to add the currents. Okay. If you are assuming the current direction as an clockwise direction, then it will always flow in the opposite direction. Okay. And we can write the difference in current. So now we are writing the equation for loop 1. So this I1 current should come first. Minus I2. Okay. That will be equal to 0. Now here there will be another one element that is called R2. R2 will be, what about the voltage drop across R2? Plus to minus, it will be minus R2 into, here there will be a two current similar to this R3. So we have to write the difference in currents. Okay, I1 minus I2. Okay, because we are writing the equation for loop 1. So the loop 1 current should come first. Okay, so in this way we can complete this equation. So, and none of the elements hereafter, isn't it? So we can write this is equal to 0. So now in each and every element we have minus sign, isn't it? All are voltage drops. So throughout, if you are multiplying with minus sign, all the terms becomes plus. Okay. Now we can represent it as equation 4. Okay. Already we have 3 equations in a mechanical translational system. Okay. Now this is the first equation we obtained in an electrical system. Now for loop 2, we are going to apply Kirchhoff's voltage law. Okay. So here we can start it from here, this corner. Okay. If you are going from plus to minus, it will be minus. What about the voltage drop across the inductor? L into di by dt. Here it will be L2 into di2 by dt, because I2 is the only current flowing through this L2. Okay. Then here, if you are coming like this, from plus to minus, it will be minus. Okay. So minus R2 into, what about the current? Difference in current, that is I2 minus I1. Now we are writing the equation for loop 2. So this I2 current should come first. Okay, I2 minus I1. Then minus, the next plus to minus will be minus. Then what about the voltage drop across the resistor? R into I. Okay, R23 into, here also two currents, I2 as well as I3. Okay, so we have to write the difference in currents I2 minus I3, because we are writing the equation for loop 2. Okay, so loop 2 current should come first. Then again, from plus to minus, it will be minus. Voltage drop across the capacitor, 1 by C23 into integral, the difference in current, that is I2 minus I3. That is the current for loop current for this loop 2 minus the loop current for loop 3. Okay, into dt will be equal to 0. Here also there is no voltage rise, all are voltage drop. Okay, in all the terms we have minus sign, so throughout we can multiply with minus, so we will get the equation like this. So we can represent it as equation number 5. Okay, so now for loop 3 we have to apply Kirchhoff's voltage law. So this is loop 3. Okay, so we can start it from here. Okay, if you are going like this, plus to minus, it will be minus L3 into, what's the formula? L3 into di by dt, di3 divided by dt. Okay, first term. Then if you are going like this, from plus to minus, it will be minus. What about the voltage drop across the capacitor? 1 by C into integral I dt. That is 1 by C23 into integral. Here the current will be a difference in current, because both the currents are flowing in the opposite direction. But we have to write the I3 current first. Because we are writing the equation for loop 3. Okay, I3 minus I2. Now the next element will be R23. If you are going from plus to minus, it will be minus R23 into, here also difference in current, but we have to write this I3 current first. Okay, I3 minus I2. Now if you are coming like this, again it is plus to minus, so we have to put a minus sign, and R3 into, here also there will be a difference in current, I3 minus I1. Okay, because we are writing the equation for loop 3. Okay, I3 minus I1 equal to 0. Okay, so now here also in all the terms we have minus sign, so throughout we can multiply it with minus, so we will get the expression like this. Okay, this will be an equation 6. Understood? Now we have to compare this 4, 5 and 6 with the equation which is obtained in the mechanical translational system, that is differential equation 1, 2 and 3. That differential equation 1 will be equivalent to this 4. Okay, differential equation 1 represents the differential equation for mass M1. So correspondingly here we have the equation for loop 1. So these two will be similar. Similarly, differential equation for mass M2 will be equivalent to the equation for loop 2. These two will be similar. Okay. Similarly, the third equation will be similar to the equation which is obtained for loop 3. Okay. So we can write the equation 4, 5 and 6 are similar to the equation 1, 2 and 3 respectively. Okay. Now we are going to see the next analogous circuit, that is nothing but force to current analogy. Okay, so now for force to current analogy, first we have to write the formula. So this is the formula for force to current analogy. Okay, so from the question, so this is the question. From the question, we have to draw the force to current analogous circuit. This is the force to current analogous circuit. How to draw this circuit? So in force to current analogy, we have to assume nodes for each and every masses. Okay, here we have 3 masses, M1, M2 as well as M3. Correspondingly, here we have to assume 3 number of nodes. Node 1 and the corresponding voltage will be V1, node 2 and the corresponding voltage will be V2, node 3 and the corresponding voltage will be V3. So in the sequence, in the order, we have to assume 3 number of nodes. Okay, in all the problems, always one after the other, we have to assume the nodes in force to voltage analogy. Whatever may be the structure of the mass in the question, we have to assume one after the other, all the masses. Okay, then only we can connect each and every element in between that node as well as ground. Understood? So for node 1, we have to put a line like this. Then only we can connect the different elements. For node 2, we have to put a small line like this, and the voltage will be V2. For node 3 also, we have to put a small line like this. Okay, and we have to draw the reference node, that is nothing but ground node. Now we can connect each and every element one by one. Okay, so first we can see the mass M1. For mass M1, there is no applied force, isn't it? So here this node corresponds to mass M1. There is no applied force, so there will not be any current sources here. Force corresponds to current source, so no need to connect the current source here. Okay, then we have to see all the opposing forces. Due to mass M1, there will be an opposing force. Okay, mass M corresponds to capacitor, isn't it? So we have to draw a capacitor here. So this is only for mass M1. So we have to connect it between V1 as well as ground. Okay. So it is not possible to connect an element, that is capacitor, at a particular node. That is a single node, isn't it? Only in between the two nodes we can connect the elements. Okay. So for that we have to use this ground node. Okay. Now this is due to mass M1. Now what are the elements which is connected only to this mass M1? K1 as well as B1. K corresponds to L. Okay, L1. B corresponds to R. That is R1. Okay, so here it will be L1 and here it will be R1. These three elements should be connected between the node B1 as well as ground. Okay, it is not related to any of the other nodes. Okay, now what are the elements which are connected between M1, M2 as well as M3? Okay, between M1 as well as M2 we have B2. Okay, the corresponding opposing force will be FB2. B corresponds to R. Okay, in between M1 as well as, that is node 1 as well as node 2, we have B. Okay, B2. B corresponds to R, so it will be R2. Understood? Now, in between node M1 as well as M3, we have B3. Okay, B corresponds to R, isn't it? So, in between 1 and 3, we have the resistor R3. Okay, so these are all the different elements connected to this M1. Understood? Now we have to consider the node 2. So for that we have to see this mass M2. For this mass M2 there is no applied force. So in this node there will not be any current source. Okay. Now what about the own opposing force due to M2? Okay, M corresponds to C. So capacitor should be drawn at this node 2 between node 2 as well as ground. Okay. Now only to this mass M2 there is none of the elements. Okay, now we have to see all the remaining elements. K23, B23. These two are connected between M2 as well as M3. Okay, so this is M2. Now for this mass M between M2, that is node 2 as well as node 3, we are going to connect this K23 as well as B23. What is K23 corresponds to? K corresponds to L. So we have to draw this L23. Then B23. It is also between M2 as well as M3. B corresponds to R. So in between node 2 and node 3, we have to connect this R23. Okay, so L23 as well as R23 are connected between node 2 as well as node 3. Okay. Now, is there any other elements for this mass M2? This B2. This B2 is already connected, isn't it? While drawing the diagram for this mass M1. Okay, in between M1 and M2 there will be an B2. B corresponds to R. It is already connected, so no need to connect it again. Okay, so in this way we can connect each and every element for this mass M2. Okay, now consider this node 3. To connect different elements in node 3, what we have to do? We have to see this mass M3. So in this mass M3, if there is any applied force, there is no applied force. Okay, no need to draw any current sources here. Okay, if you are having any applied force, force corresponds to current. So here you have to draw the current source. Here no need to draw the current source at node 3. Now what are the opposing forces in node that is for mass M3? There will be an own opposing force due to M3. Okay, so this M corresponds to C. So here we have to represent the capacitor C3. Okay, in between node 3 as well as ground. Okay, then what are the elements connected only to this M3? None of the elements. Okay, this B2, that is B3 is connected between M3 as well as M1. Okay, so B corresponds to R, isn't it? So B3 will be R3. R3 is already connected between M1 as well as M3. So no need to draw it again. Okay. Now if you are considering K23 as well as B23, the corresponding elements R23 as well as L23 are already connected. Okay, while drawing the diagram for M2, no need to connect it again. Okay, so these are all the different components related to this mass M3. Okay, in this way we have to complete the diagrams. After that, what we have to do is we have to assume the direction of current for each and every node. Okay, here this is an force to current analogy. We are going to apply Kirchhoff's current law, isn't it? To apply Kirchhoff's current law at each and every node, we need a current direction. In the previous case, that is force to voltage analogy, while applying the Kirchhoff's voltage law, we need to assume an loop current. Okay. So here at each and every node, we have to assume the node current. Okay. So how to assume the node current? We are assuming the direction of node current. Okay. So here in this node 1, there is no source. Okay. That is current source. So all the elements are except that current source, that is none of the current sources are connected here. Through all these elements there will be an current. Okay, so we have to assume all the currents are outflowing currents. Okay, there is none of the incoming current. That's the meaning. Suppose if you have a current source here, from the current source there will be an incoming current to this node 1, but here there is no current source, all are outgoing current. Okay, always we have to assume the current which is away from the node. Okay, totally 5 branches are connected here, 5 number of outgoing currents. Similarly for node 2, there is no source, so there will not be any incoming current. 4 number of branches are there, that is 4 elements. For all the elements you have to assume the outgoing current. And similarly for node 3, there is no incoming current because there is no source here. Then through all the 4 elements there will be an outgoing current. Okay, so if you are considering this R2, there will be a current in this direction and also in this direction. Okay, while writing the equation for node 1, we have to assume this direction. While writing the equation for node 2, we have to assume this direction. Okay, now we are going to write the equation by applying Kirchhoff's current law. Okay, now for this node 1, we are going to apply Kirchhoff's current law. Okay, so what is Kirchhoff's current law? The sum of the incoming current will be equal to the sum of the outgoing currents. Okay, here none of the incoming current, only all the currents are outgoing currents. Okay, so now we have to sum all the outgoing currents. Okay, we can start it from here. What about the current flowing through the capacitor C? As I told already, current flowing through the capacitor will be C into dV by dt. Okay, this V represents the voltage drop across the capacitor C. Understood? So first, the formula will be C1 into d by dt of V1. What is V1? Voltage drop across the capacitor C1. Here for capacitor C1, what will be the voltage drop? This voltage. So through this line, the voltage will be V1. V1 minus this voltage, that is 0. V1 minus 0 will be V1. So here we are writing it as V1. Okay. Then next current plus current flowing through the inductor. What's the formula? 1 by L into integral V dt. Okay. So here it is 1 by L1 into integral. What about the voltage? V1 minus 0, that is V1 into dt. Okay. The next resistor. What about the current flowing through the resistor? I is equal to V by R. Okay. That is V1 minus 0, that is an voltage. V1 divided by R1. Okay. Then next R3 resistor. Okay. That is, this is another one outgoing current. So here what will be the formula for current? I is equal to V by R. V is nothing but voltage difference between one end of R3 as well as other end of this R3. One end is connected to V1, other end is connected to V3. Okay, so V1 minus V3. So while writing the equation for this node 1, we have to assume this direction for resistor R3. Okay, so this is a higher potential and this is a lower potential. Current is always flowing from the higher potential to lower potential. So we have to write this V1 voltage first. Okay, V1 minus V3 divided by R3. Okay, the next element is R2. So here also two ends are at different potential, V1 as well as V2. Now we are writing the equation for V1, so it will be V1 minus V2 divided by R2. That's the current flowing through the resistor R2. Okay. Now sum of all these currents will be equal to 0 because at this node 1 there is no incoming current. Okay. Now similarly at node 2 as well as node 3 we can apply Kirchhoff's current law. Okay. Now see here, so this is the same diagram. That is, okay, in the previous slide we have this diagram. Okay, so this is a main diagram, force to current electrical analogous circuit. From this, at node 2, we are going to apply Kirchhoff's current law. Okay, so at this node 2, we can write the node currents one by one. Okay, so for this R2, what will be the current? Current flowing through the resistor will be V by R, that is V2 minus V1 divided by R2. Okay, V by R is nothing but difference in voltage divided by R2. So here we have to consider this current because we are writing the equation for node 2, V2 minus V1 divided by R2. Okay, then plus, what about the next current? If you are considering C2, the current will be C into dV by dt. So here C2 into dV2 by dt because C2 is connected between V2 as well as 0 volt. That is ground. Okay. So V2 minus 0 will be V2 divided by dt. Okay. The next element will be this R23. Okay. For R23, what will be the difference in voltage? V2 minus V3 divided by R23. Okay. Next for L23. For L23, what is the formula? For current 1 by L23 into integral V2 minus V3 dt. Okay. That will be equal to 0. So this is the node equation at the node 2. Similarly, we have to write the equation for node 3 by applying Kirchhoff's current law. Okay. At node 3, so first we can write this R3. Okay. So R3 will be, what's the current flowing through this R3? The voltage drop across R3 divided by R3 value. So here we have to assume this direction, that is this arrow, from V3 to node V1. So the voltage drop will be across this R3 will be V3 minus V1 divided by R3. Okay, that's the first current. Then if you are considering R23, what will be the drop across R23? V3 minus V2 divided by R23. Okay, that will be the current. Okay, the next L23. What's the formula for current flowing through the inductor? 1 by L23 into integral. Current is flowing in this direction. Okay, we have to assume this current. Okay, V2 minus V3 minus V2 into dt. Okay, the formula for current flowing through the inductor is 1 by L into integral V dt. Here the value of L is 1, that is L23. That is 1 by L23 in the integral. V is nothing but voltage drop across L23. That is V3 minus V2 into dt. Okay. So the last element is C3. Current flowing through the C3. What is the current flowing through the C3? C3 into, according to this formula, C3 into dV3 divided by dt. Here, voltage drop across the C3 will be V3 minus 0. Okay, so directly we can write it as V3. dV3 divided by dt is equal to 0. None of the incoming current, so the right side will be 0. Okay, in this way, we will get 3 number of node equations by using Kirchhoff's current law. Okay, 3 equations are equations 7, 8 and 9. Okay, all these 3 equations will be similar to the differential equation we have derived in mechanical translational system, that is equation 1, 2 and 3. Finally, you have to write equation 7, 8 and 9 are similar to equation 1, 2 and 3 respectively. Okay. So this is about the problems in the electrical analogous to mechanical translational systems. Okay, if you know the formula, we can easily obtain the electrical analogous circuit and also all the equations for voltage as well as currents. Okay. The next homework, electrical analogous to mechanical translational system. we are obtaining force to voltage as well as force to current analogous circuit, isn't it? Here, one mechanical system is given. So this is a mechanical translational system. So from the diagram, we can easily identify it as a mechanical translational system. Here we are going to find out force to voltage as well as force to current analogous circuit. Okay. So here three masses are there, M1, M2 as well as M3, as well as two inputs are there, F1 of t as well as F2 of t. Okay. So while drawing force to voltage analogy, you will be having three number of loops sequentially. Okay. For each loop, if there is any applied force, correspondingly you have to draw the voltage source. Okay. Here in the first loop, you will have an voltage source V1. In the second loop, you will have an voltage source V2 corresponding to this force F2. Okay. In the last loop, there will not be any voltage source. Okay. Similarly, while drawing this force to current analogy, in the first node, you will be having a current source. Similarly, in the second node, you will be having a current source corresponding to F2. In the last node, you will not be having any current source. Understood? So you can easily complete this diagram as well as you can obtain the electrical analogous circuit. Now, the second problem is electrical analogous circuit for a mechanical translational system. Here with two masses, that is M1 as well as M2, there will be an friction between M1 as well as fixed surface, that is represented by the letter B1. Okay, it is not represented by using its symbol. Okay, here also in between M2 as well as reference surface, there will be a friction that is represented by a letter B2. Okay, here you are asked to find the electrical analogous circuit. Electrical analogous circuit means two circuit you have to find out. Force to voltage analogous circuit as well as force to current electrical analogous circuit. Okay, rest we shall see in the next class. Thank you.